Alright, another draft science video. This time on the message board thing, the bulletin board anyway, and for the purpose of segmenting as best as possible these different subjects, even though they all do blend into each other, especially when one is proposing something called the unification theory. Yeah, it would make sense that they blend all together. So anyway, the general subject of quantum mechanics, so much mystique, claim to be there's so much like such a superior form of logic or a way of looking at the world or the universe, a way of totally insulting something called the past and the silly classical way of looking at things, and it's just this as if there's a it is a fundamentally different way, but the way is a loose kind of science, in my opinion, and that's what the difference is. A science where imagination is glorified, instead of appreciated and understood to be the process through which you use to understand, is to imagine the function and to model what you can of it. Alright, so the real point is this is about the smallest things in the universe, the hardest things in the universe to actually observe without interfering with them. So it's very difficult to know what they are because there's no ruler small enough to measure them by. There's no way to, can't videotape them. It's almost, they're almost as inaccessible as some elements of history. There's just no fingerprints, no evidence left behind, kind of a thing. And these little tiny bits leave big blobs of evidence, but they don't leave a discrete fingerprint consistent with their size. You just see the shoplifting, you don't see the shoplifters. I don't know, something like that. So anyway, there's, in my opinion, just my observation, my judgment of the problem here, is that there's very soft evidence, and that's what we're stuck with. Until somebody is able to argue for a model that fits everything, that does unify, does something to substantially advance understanding of the consequences, the products of the fundamental interactions of energy and force. Yeah, we're stuck with soft evidence, but I would argue that the devotion to quantum mechanics is a hard devotion. Okay, so on soft evidence, I guess that's how I'll say it. Yeah, my talking points are a little less direct in this video, just because, like I said, it is an expansive subject. So I don't have anything wrong with the idea of quantum. That's great. The idea of quantizing energy, and I don't think there's anything about quantum mechanics that is any way, the funny parts of it have anything to do with the quantization of the energy component. The part that they've turned it into is a quantization of a kind of function. It's kind of like the time dilation thing or something. It's this way of blending some other dimensional element into the subject when we kind of know that there's nothing in the structure of quantum mechanics that violates conservation laws and the energy equations that are dependable and reliable about something doesn't come from nothing kind of idea isn't violated by quantum mechanics. And so I'd say that the energy component, the quantum part, is fine. It's the it's the idea of talking about why there are certain irregularities, probably the wrong word. Anyway, so a model of shape and function is what we're after. And the problem, I guess, is that we have some element of function and some element of shape, and it's just not enough. And so I think the two things get confused. People end up thinking the function has something to do with the shape, or the shape has something to do with the function. And sometimes it doesn't. It's the environment. It's the shape. I guess the argument is there's two shapes here to the byproduct of function. There's the thing and the thing it's interacting with. And that's what we're talking about. It's interactions. And if I was to simplify quantum mechanics, I would argue that what quantum mechanics has done, as quantum mechanics as they claim ownership of the concept, which is the spooky action stuff, the wave functions, that kind of stuff. It's the model is basically saying something like, well, here you have the elemental bit, the quanta of energy, and we sort of know that's kind of described as a photon. There's nothing really less energetic than this thing as far as we know. And it comes in this various forms, which there's also associated with energy, which I think it was a mistake, but I think Einstein basically was saying you can quantize this energy. Now what they turn that into is saying frequency equals energy, and what frequency really equals is amount over time, and it's always it has to be put in terms of an actual equation or function like that, because it has to be understood that you can have something at a high frequency and just a little tiny bit of it, or you can have something at a low frequency but you have a lot of it, and volume's going to matter to what would be a real energy equation. So frequency only equals energy when you're comparing equal volumes of time, and equal the switch is on the whole time. So if you're comparing it like light bulbs, infrared light bulb, ultraviolet light bulb, and they're on the same amount of time, yes, there'll be more energy in the ultraviolet light, but that's only because it's producing more photons every second. It's a volume equation. Anyway, so this gets to the subject, which is, as I was trying to get to the point, so the real nature of quantum mechanics is you have two things. You have the little thing that's interacting with the world, the photon or the electron. Both things we can't really see. You can't even bounce photons off of an electron without interfering with it pretty substantially. So there's nothing we can bounce off of it to resolve its place in the universe or what it looks like or what it's doing. But the point is so you have two things. You have these little tiny bits, and then you have this structure of environment that has all the forces in it, gravity, electromagnetism, plus the matter itself. And quantum mechanics has basically decided to say that anything weird that happens when these two things interact, when you take this little tiny bit and interact it with this more complex environment, that the complexity of any outcome, any confusion or weirdness in the product you get, is a function of the little bit. The little bit has the properties, and it's the environment that's kind of dead and flat and predictable. So they create an environment that's classically dull and blurry and has no irregularities, and then they create a thing, a super ball to bounce on it, that's convoluted and crooked and bent and warped. And so by simplest description, I'd say it's like the argument I've made for gravity and bent space, that it's more sensible to go with push than pull. And in this case of quantum mechanics, it would be more sensible to try to make the convoluted environment being the interactor, being the aggressor in the interaction, being the one that has the spikes and the irregularities, the regular irregularities, rather than the simple thing that from all evidence outside of this stuff, the environment, put it in a clean environment, and what does it seem to do? It seems to do the same thing over and over and over again very reliably. It moves in a straight line the speed of light. It doesn't do anything else. And if it does anything else, you'll usually find environment somewhere near, especially with electrons. Electrons are totally owned by the ghost of environment, so to speak. So I'm just saying that, in my opinion, it's a failure of the advocates of quantum mechanics to first recognize their evidence is very weak, and then to accept that they're really challenging a fundamentally reasonable proposition, which is, it seems like kind of an extraordinary thing to be blaming the thing that's simpler for the complexity in the interaction. If you have two things in an interaction, a complex thing and a very simple thing, it's kind of extraordinary to say the simple thing is the one creating all the bizarreness or the wackiness. And that, I would argue, is the failure of quantum theory as an explanation of shape and function. The environment's causing the effects. So anyway, so I guess I would argue that they have left classical models of physics retarded and unimproved. So you could argue that Einstein fixed a little bit of a simplification in Newton. Newton basically said, look, gravity, the force of gravity, let's just combine the two bodies, m1, m2 in the formula, and we'll just do a net equation. When the real effect is the Earth causes gravity to happen to the sun, and the sun causes gravity to happen to the Earth, and the two really don't mix, and they're really two different forces, and they affect each other differently. And Einstein pulled that detail out of the classical model. Now, he didn't need to use bent space, in my opinion, to do it. He just had to recognize there's such a thing as the speed of gravity, and that the two effects are separate effects, and you need a more complex equation to be able to calculate their interaction, because as each one's acting, the other one's acting, and that creates a very complex equation for that dance. That dance, if looked at as not just an end product, has a lot more irregularity in it. And so anyway, that's a simple point being made here, is the classical model wasn't fundamentally broken, it just lacked a little bit of maturity. It didn't know the speed of light, it didn't know some things. And I would argue that this model of classical physics that they use to make quantum mechanics seem so much better is a model they won't let grow anywhere from where it was 300 years ago. So if you add anything to the classical model, any understanding that there's a more complex detail, that there are atoms, and the atoms have electrons and protons and neutrons, you're not even allowed to do anything but keep everything into dull spheres with certain properties. So the classical model isn't allowed to incorporate anything we have learned, and to be a more competitive model. They just keep it old, archaic, and unimproved. And that's such a cheat to make a comparison like that. Alright, so then we get into probability of an event or outcome, and that quantum mechanics does some good math to take what we can observe and understand that there are certain regularities in it, to find those and to be able to formalize them into mathematics. Nothing wrong with doing probability studies. You can do it with the thing called culture. You could take our society and you could do studies on outcomes. Now that's not exactly going to tell you causes, and you may be able to predict the future based on past trends, but again, it's not telling you why it's happening. And it's foolish to sit there and say because it's bad water causes one effect. Polluted water, you could say in the 70s the water was very polluted, and so then you could blame something like income taxes, higher income taxes on the polluted water. And you could say the water's cleaner now, and we have lower income taxes on the rich. And you could associate those things. But I don't think it would be reasonable to do so. I don't think you'll be able to make any evidence to say, I know this is the causation. But that's what they've done here, because they find a statistical comparison, something, a fact that's similar somewhere else at the same circumstantial time. They'll say, okay, these two things are necessarily related, when they're not necessarily related. Okay. The structure of interaction has hidden regular irregularities and unseen, undiscovered event contours and variables. So yes, I'm arguing that not so much for a hidden variable, undiscovered variables. And so I could use a simple analogy of the two-slit experiment or a surface reflection experiment or any one of these. The assumption in all these experiments is that the thing being interacted with, like two material slits, are the surface of glass, but these things are flat, dull, consistent. They're as smooth as something's butt, and all of that kind of stuff. And the assumption is that all the power and all the magic is in where the photon is and what it's doing, rather than recognizing that all you have to do is create some contour on the surface of the glass. Let's say something simple. I could make, let's say you're doing experiments, okay, and you're bouncing little round balls that are all the same, and you're bouncing them off a surface. And so I change the surface by putting a lot of little pyramids on the surface. Well, and then you'll notice when you throw the ball that sometimes it bounces back because it hits the surface of the pyramid. And there'll be a certain statistical probability of this outcome, that the ball bounces back because it doesn't hit the top of the pyramids all the time, and so it doesn't bounce forward. And depending on where the slope of the pyramid is, it bounces somewhere different. And it'll have a probability curve. But if there's a bunch of pyramids, you can understand that that probability curve will just be replayed by the irregularity of where you throw the ball and how far you throw it. How far away the slope is will change the angle that it leaves, and it'll change the place it lands. But now let's just say I change that experiment, make it little staircases. So they're not pyramids now, they're staircases. Like the real pyramids. You know, they have a leasing on them. They have a more complexity to their surface. Well, now you can understand that now you're going to get all kinds of weird bounces, because now the ball is going to hit the flat surface, or it's going to hit the vertical surface and bounce off the flat surface. It's going to do lots of different things, but there's still going to be a probability. There's still going to be a factual circumstance where if I randomly, as best possible to synthesize, if I synthesize random projection of the ball onto that field, there'll be definite statistical outcomes decided by just that structure. And I would argue that what we see in most of what are defined as the experiments of quantum mechanics, the ones demonstrating or proving wave-like behavior, are just that. They're just experiments that are demonstrating the complexity of the surface you're throwing this simple thing at. And the fact is it has a regular irregularity. And that's the undiscovered variable. I would argue I've discovered some of it. I think it's in the function of the electron, and the fact that electrons are in a matrix, a rigid. They have to conform to the matter they're part of, and they will behave in very predictable and consistent ways in different fields. And when they are loose electrons around surfaces, usually called charge, in the form of charge, they have a certain configuration, and when they're built into the actual matter, they have another configuration. But most of the time, any light heading for a surface is going to interact with the layer of electrons that are in the loose field, the charge field, around any material surface. And I would argue that every material surface has this charge field, merely because the protons produce more attractive force, then they can capture objects. So like our solar system, it's probably possible that another planet could exist outside of Pluto. There's room for there's gravity still out there that's not being used. But it might not be strong enough to keep something in an orbit. It might just be strong enough to bend something. And that would be the key factor of these electrons. They're not bound to the atoms, but they are, they like them. They're going to hang around. They're going to stay in the vicinity. And in my opinion, that's enough of a physical explanation, enough of an indication of a potential cause for the quantum effects that parallel, just in the simplest and crudest way, some of the classical quantum effects like wave interference. So in a couple of circumstances there's a similarity with wave interference in mediums, but that is, as I've argued and will continue to argue, it's pretty much the simplest pattern you can create, which is an on-off pattern. And there's not much parallel between the rest of physics in terms of finding wave function in these small quanta. They don't in any other way behave wave-like, in that they don't appear to spread in any medium. They don't arrive in destinations where quantum effects aren't going to happen in any kind of wave way. They arrive as discrete bits of energy. Anyway, so the real point is that quantum mechanics is a formalization of the idea, okay, that there is a pattern built into structure. And the point is the pattern a waving fundamental particle, or is the pattern part of a repeating structure built into material having to conform to the rules of atomic structure and the combination of atoms, the rules of material formulation, maintenance. Maybe that's a good word, maintenance. And that you're just recycling. And that's the Feynman clock is just, the point of it is just to see, as time changes, you will recycle through the same vectors. You'll hit the same staircases, and you'll hit it in different places based on the same random equation. There's just as much likelihood you'll hit stair 1 as stair 10 in each single case of each staircase. And that's what Feynman's math is essentially duplicating, is just the fact that you're going through, as you go all the way for a certain distance in time, you bounce into the next staircase. You go into the next staircase. You reach the next segment of pattern. Alright, let's see. Obey rules, tendencies, potentials. Well, that's, it's just, obviously it's just saying I'm not going to disagree with the outcomes of experiments. I'm going to disagree with the interpretation of the cause for the effect. And I again argue that it's, in my opinion, fundamentally illogical to think we should be weighted towards finding reasons why photons have magical powers rather than finding reasons why matter affects environments. That matter is leaking fields of force. Alright, there are limits to perception with which quantities can be known, and that's the real problem here. It's just, this is the smallest stuff in the universe. You can't really see it, so you have to dissect what it's doing based on its effects. And I'm just saying, what we have as evidence is that we know we have a little thing, and we know it's interacting with a much bigger thing. And my argument is it's more sensible to figure out possible ways the big thing is causing the little thing to act a certain way. All right, wacky behavior, this is known as, obviously there's nothing, it's only wacky because it's a misunderstood. Very specifically developed mathematical formulas. Again, I don't have any objection to probability theory. It's perfectly rational to recognize patterns and to formalize them into math. But when you say the actual function of the probability is in some sort of, the photon is is making up fake stairs to bounce irregularly off of, that the photon somehow has the wackiness, the pattern built into it, I think is wrong-headed. Various specific, let's see, the wave function. Probability, amplitude, let's see, probability, amplitude of position, momentum, and other physical properties of a particle. Amplitude of position, momentum, other, yeah, so this problem is just a measurement problem, and they're arguing quite aggressively that no, it doesn't have anything to do with measurement. It has to do with the fact that the particle is unmeasurable. No, it's worse than that. It is not in a place. So it just seems kind of coincidental that the one thing in the universe we can't see is the one thing in the universe that's doing something purely random. We can't find a pure random anywhere else in the universe except in this thing smaller, the smallest thing in the universe. It just seems kind of a coincidence or a convenience for somebody advocating such a theory that this is where this is the place it's going to be, the one place we can't test the theory. It's like God living in a house we can't, he lives somewhere we can't see him. Well, how convenient is that? Yeah, that sure does make it convenient for those who want to explain why he exists when there's no evidence of him existing. So anyway, so here's an Einstein kind of quote from, I think, Wikipedia or something. Einstein further developed this idea to show that an electromagnetic wave, such as light, could also be described as a particle. So again, this is, I think, Einstein's true perspective, is that there has to be, even in his bent space, it's a rigid rule-based system. It does not have any magical property, later called a photon, with a discrete quantum of energy. So it's this idea, at least the part of quantum mechanics I don't think they can break, is the idea that we can quantize or establish the energy component and say that doesn't do any of this silliness. Okay, and I'd say frequency is more sensibly understood as a quantity over time, so I think I already made that point. The quantum mechanical atomic model has succeeded spectacularly, this is the words from Wikipedia, in the realms where classical mechanics and magnetism falter, and classic physics cannot account for. And then they give a list of the well, I'll do that second. Let me do this idea of succeeding spectacularly against a classical model they don't let mature, and that's the real problem here. Quantum mechanics does not so spectacular once you have a classical model of electromagnetism that allows for the virtual photon, that does create a simple force that conveys the energy from one place to the other. And once you allow for that mechanism is a very competitive, not only for explanation purposes but for modeling purposes. It allows you to very accurately model the function of magnets. Alright, so classical physics cannot account for quantization of certain physical properties. Can't even say what that means as a statement. So I just ignore it because that doesn't even say anything. Quantum entanglement. Well, why would it account for something that doesn't exist? The principle of uncertainty. Again, why would it account for a notion that instead of conceding that you can't measure the smallest things in the universe, instead you're going to say they don't have a length, width, or height. You can't measure them, you can't see them, and because they're invisible just because of mechanical impossibility, you'll claim it's not mechanical impossibility, it's because they're invisible, essentially. That they have no reality or something. Again, a totally unnecessary conclusion. Wave-particle duality, well again, why would classical physics bother with wave? Because it knows that's a medium function, and there's no description of a medium in any of quantum mechanics. So what are they playing with that concept for? But yeah, I have heard them do this. They'll talk about the electromagnetic field, and they're actually talking about it being an existing field. Okay, that there's not a something moving a thing, a ton, a carrier of force, but that somehow there's this field that stuff vibrates, the field, to get from one place to another. So quantum mechanics is turning into ether theory quite quickly. Alright, and that is dependent on frequency. Well, no, I think those are just bad notes. So anyway, like I said, I think the other subjects will be actually easier for me to do real, here's my better alternative explanation, because everything is specific to this, in the sense that obviously I'm arguing for a particle force, that all the forces are made of this quanta, and you can see it. Okay, the Earth moves into the sun because it's hit with energy that pushes it into the sun. That's a fact. An imbalance in the field of these little bits. More rain on one side than the other, however you want to metaphor it. More water density, more pressure. That there's pressure gradients in this field of energy. And it's real stuff hitting real stuff in the end. But the thing that we are made out of is pattern, and the pattern just is the important thing in terms of understanding what momentum is and some of these other subjects. But yes, they're real discrete bits. Like I said, I don't care whether you make them out of marble, or ivory, like a cue ball. It doesn't really matter what you make them out of. They are cue balls. They are checkers. And there's red checkers and black checkers, but there's just checkers. And they move at a very consistent and dependable manner. And the only thing that gets tricky is that when one checker heads for a big pile of checkers, interactions can get a little funky. Alright, but no need to create mysticism and magic and to give the simplest things in the universe a bunch of properties they don't have. Alright, but like I said, it gets into everything. It's magnetism, electricity, gravity, all these things are the same thing. And once that's understood, there's no need for any of this wave theory, because you'll understand what a wave is, which is it's just a mass of quanta moving. Quanta of a specific polarization, a material pile of quanta. Waves don't happen anywhere else. Okay, that's enough. So, till next time, and such.